So angular velocity and displacement. See, just like we consider for a linear motion. For a linear motion, we know that when an object moves, it has a linear displacement, it has a velocity also. So as of now, earlier we were using just the terms as velocity and displacement, as we are not going much into the circular motion. So when we go into circular motion means if an object revolves or rotates about an axis, or if an object moves in a circle, we call this as a circular motion. So during a circular motion, an object covers angular displacements. An object moves in a circle. So if an object is moving in a circle, it covers angular displacement. So let us say here circular motion. So during circular motion, what is circular motion? We have when an object moves in a circular path, moves in a circular path, it is called circular motion. Now, the kinematics of the circular motion, they are quite similar to the linear motion only, provided with a little bit of differences. So, let's see, let's have an object moving in a circular path. Hello, Jaswant.
Yes, sir.
So just giving you a quick revision and then we will move further about the angular velocity and its kinematics. So here in a plane, in this plane where I can describe the axis, where I can have the x-axis and y-axis. So in this plane, we have an object which is moving in a circle. So here the object is moving in a circle. It is following a circular path with center C. So it has center over here at C. It follows a circular path. So when it's moving in a circular path, I told you that it has two directions of motion which are possible. Okay. So the two directions of motion which are possible, it can be either anti-clockwise motion or it can be a clockwise motion. Anti-clockwise or clockwise. So the yesterday we discussed that anti-clockwise motion, here if there is any displacement in the anti-clockwise direction, we will take it to be the positive. And if there is any displacement along the clockwise, we will take it to be the negative. So suppose if from this point P, the object moves in the anti-clockwise direction, and after some time it has traveled through certain displacement, and now it is at point A. So we will say that this angular displacement PA, it has made an angular displacement PA, it has made an angular displacement PA, and this is a positive angular displacement. Right. Also, I told you that for representation, we take the direction of this since it is a vector quantity. We know that displacement is a vector quantity. So we also consider the angular displacement to be the vector quantity, and direction of this angular displacement is taken along the axis about which it is rotating. So if it is positive, that means we consider it on the upward side. If it is negative, we consider it in the downside. Okay. So that is how we consider the dynamics of the circular motion. Also, we had discussed that angular displacement will be given by the letter theta. So angular displacement, it was given by letter theta, and its SI units were radian. Okay. So SI units for angular displacement is radian. It is measured in radian. And I talked of angular velocity. So angular velocity given by the symbol omega. It's given by the symbol omega and it is equal to theta by t. So as you move further in mathematics, we will also denote this angular velocity over change of time. Okay. Moving more into the depth, if you move to the instantaneous velocity, so we will be writing it as d theta by dt. You will write it something like this, d theta over dt.
Hello, hello.
There was just one network issue. So that was at the meeting, I think, put all of you in waiting room.
Yes.
Just one is also joining. Yeah. So here we were here. Just one you have joined. Just one.
Yes, sir.
Okay. So see here, we were talking of the angular velocity. The angular velocity is given by the symbol omega. Its SI unit was radian per second. So we had found out yesterday. One more thing we had discussed yesterday about the angular frequency. This see now these are the two words. If you just talk of frequency, okay. So frequency is what the number of vibrations per second or number of revolutions per second, right? So this frequency would be given in RPM, revolutions per minute, or revolutions per second, RPS. These are the general common words that will be used to describe this frequency, or you will be using the SI unit hertz. But at the same time, if you are given the word angular frequency, see, the angular frequency is the same as angular velocity. Okay, angular frequency means angular velocity, they are the same. There is no difference between them. Okay. So how is angular velocity omega related with general frequency? We can relate omega with general frequency by the formula 2 pi f. This I told you yesterday that angular velocity omega can be related with frequency. F is the frequency, not the angular frequency. So it is related by the formula omega will be equal to 2 pi f. Understood this? Okay. Now, just like for the linear motion, we have linear acceleration. So we have studied that acceleration is given by the formula. We have said that acceleration is given by the formula v minus u over t. Okay, this is how the angle. This is how the acceleration is given for a particle which is moving. Now, if an particle is moving in a circle, so suppose initially it starts its rotation and then it increases its speed. So as it increases its speed, it will be covering the angles faster. So just like the linear motion, we can also describe the angular motion. We can also have the angular acceleration. Okay, so similar to this, you have an angular acceleration also. So you will have angular acceleration, and in angular acceleration, the symbol will be alpha. Alpha will represent the angular acceleration, and it would be given by the same thing: final angular velocity minus initial angular velocity divided by t. The same thing. Almost the same thing. The terms have changed. Omega means omega is now your final angular velocity. This is your final angular velocity, and omega naught is the initial angular velocity. Initial angular velocity. And alpha is the angular acceleration. Alpha is angular acceleration. So this is angular acceleration. Now, in the same way, we have the kinematics for the angular motion. Like for the linear motion, we have the kinematics. We have the kinematic equations given by v equals u plus at. We have s equals ut plus 1 by 2 at squared. We have the third equation given as v squared minus u squared equals to 2as, right? We have these three kinematic equations of motion. Now, similar to this, we have kinematic equations of motion for the angular motion. So, for the angular motion, you will have your first equation, or you can say first equation of motion would be written as omega equals to omega naught plus alpha t. Okay. Then we have angular displacement theta. So we have theta is equal to omega naught t plus 1 by 2 alpha t squared. Then the third one will be omega squared minus omega naught squared will be equal to 2 alpha theta. So just compare with their counterparts in the linear motion.
What do you mean by that alpha or
Yeah,
what do you mean by alpha over there?
alpha is the angular acceleration. How fast it is increasing its angular velocity. So if an object is moving in a circle, suppose it starts from its zero angular velocity, then it increases its angular speed.
Hmm.
Okay. So if it is increasing its angular speed, how fast is it? How fast is it increasing its angular speed? Okay.
Sir,
So
can you
that
show
how,
the previous slide?
yes,
Can you show the previous page?
yeah, yeah. You have alpha or angular acceleration. It's similar to the linear acceleration. Like the linear acceleration is v minus u over t. Here the angular acceleration alpha is given by omega minus omega naught over t.
Okay.
Okay. For most of the cases, if you are given a uniform angular motion, if you are given the uniform angular motion, so you will be using the direct relationship that you studied. You will be using your omega equals to theta by t. But if it is an accelerated motion, if the angular motion is accelerated, so you will use these kinematic equations of motion. Okay. So let us try to use these kinematic equations of motion using a simple question. So let's have, and then I'll also tell you that how the angular velocity can be related with the linear velocity, how it can relate with the linear velocity. For example, if you see the wheels of a car moving, right? So the wheels of the car which move, those wheels of the car, they are actually revolving, they are rotating, they are making circular motion, right? Wheels are making circular motion. Okay. But when they are placed on road, they are creating a linear motion. Okay. So basically we have that how linear motion can be converted, or to how angular motion can be converted to the linear motion, and how it is related with the linear motion. Okay. So here we do a small question. Let's see. Uh, a spot on a wheel starts to rotate with starts to rotate from stationary starts to rotate from stationary position and an angular velocity of attains an angular velocity of 20 radian per second in 3 seconds, in 4 seconds. Okay. So find the angular acceleration. You have to find these things. Find the angular acceleration, angular displacement, so these two things you have to find out. You have to find out the angular acceleration, you have to find out the angular displacement. Okay. So what all things are given here in this question?
Initial angular velocity 0,
Yeah, initial angular velocity omega naught, which is 0 radian per second.
and the final is
Hmm.
20 radian per second,
Okay, final is 20 radian per second. Very good.
and time is
And
4 seconds.
time is 4 seconds, right? So we can find out, we are supposed to find out alpha and theta. This is what you are supposed to find. You are supposed to find alpha and theta. So find these out. Which formula to be used?
So angular velocity,
Hmm.
final angular velocity minus initial by time.
Yeah. So we can use that final minus initial over time. So 20 minus 0 over 4. It's 20 minus 0 over 4. So 20 by 4. Okay. So 20 by 4 would be 5. So 5 radian per second square. This would be the value of alpha. Then once we have obtained the value of alpha, can we find out the angular displacement? Find out the angular displacement.
This is the second formula. You can
Yeah, we'll use the second formula. So use the second formula.
The
Theta
question
equals,
is first formula, right?
yeah, we find out this alpha either using the first formula. Okay, you can use the first equation to obtain this alpha. Once you obtain alpha, you can find out theta. So theta would be given by omega naught t plus 1 by
Initial is
2
zero, right?
alpha t
This
square.
one.
Yeah.
Initial is 0, right?
Yeah, initial is 0.
And the final one is 20. This be 20 plus alpha 4.
Yeah, alpha is 5. Alpha you got 5.
Yeah, like 20 plus alpha 4 is like then 20 representative to form a quadratic equation.
Here you'll get 20 theta equals to 0 plus 1 by 2 multiply alpha, which is 5 multiply 4 square. Okay, so you'll get 1 by 2 multiply 5 multiply 16. Cancel, you get 8. So you get 40 radian. So you get the angular displacement to be equal to 40 radian. Okay, can you find out the linear displacement? If I tell you to find out what will be the linear displacement, so can you find out here in the same question? Let's amend this question. Now in this question, I am giving you if the radius of wheel is if the radius of wheel is 15 centimeter. Okay, find the linear displacement. Can you do that? Let's see who can apply the brain. Okay, so is there anyone who can relate, who can think of how can we find out? Anyway,
No, sir.
So using sector formula.
sector formula. So what was the sector formula? Yeah, you are pretty close to it. Pretty close to it. Okay, don't go
So
to
sir, the
sector
arc.
formula. Here we just did theta equals L by R. Okay, in grade 11, here we did theta equals L by R. So we can find out the value of L. We can find out the value of length of R if we get R times theta. So R times theta would be equal to length of R. Okay, so R, the radius is what we have. We are just given radius as uh, 15 centimeter. So we can put here 15 multiply theta, which is 40. You will get the length that has been traveled. So 50 multiply 40, you get 600 centimeter. That means 6 meter is the length traveled by this. I hope you are getting.
Yes, sir.
Yeah. So there are many ways. And now I will tell you how the angular velocity is related with the linear velocity. How the angular velocity relates with linear velocity. That is also very important. So once you know how the angular velocity is related to linear velocity or linear speed, today I'll be sending you a few questions as homework for your practice. Your relation between angular velocity and linear velocity. So how can we relate these both angular velocity and linear velocity? See, the angular velocity is given by the symbol omega and linear velocity is given by the symbol v. So I just tell you the direct relationship. The proof we'll be discussing later. Once you once you are completely in grade 11, once we start with again. So you will have whatever we can just discuss of their derivations. For now, we have linear velocity v can be given as r omega. It can be obtained by the formula R omega. How we got it? This is also a single step. You can get this. As we just have the formula theta, we had theta equals L over R. Okay, where length of arc is the actual radius. Length of arc is the actual distance that the object will be traveling. If an object is having larger wheels, so it will cover larger distances. That is how the length traveled by a wheel in one revolution, or the distance traveled by a wheel in one revolution, will be equal to the circumference of the wheel, right? So therefore, we can say that the length of arc will be equal to the linear displacement, and hence we can write this at r times theta will be equal to L. Now, if we divide both sides by t, so you will have r theta over t equals L over t. Now, r multiply theta by 2 is t is omega, and L by t is velocity. So you get the formula v equals r omega. So linear velocity can be obtained as r omega. Now, in previous question, can you find out the final velocity, final linear velocity? In this question, in the same question, can you find out the final linear velocity? Yes.
Sir, is it 300 centimeter? I mean
300.
300.
300.
Yeah. So let's see, we will be using the formula v equals r omega, and value of r is 15. Omega is given as 20 radian per second. So if you 15 multiply 20, which is 300 centimeter per second, that means you can write it as 3 meter per second, right? You have 3 meter per second as the linear velocity. So I hope you are able to understand, you are able to correlate all the things together.
Uh,
Yes?
Yes, sir.
Okay. So we'll do just a few one or two questions. See, all these are your linear velocities and linear accelerations relating with the angular one. So just hold on. I'm getting one question, one more question. Hold 1 minute. Just let me have the book. Linear. Yeah, I'm back now. So I'm giving one question from circular motion. Yeah, you have a question. What is the angular speed in radian per second of a flywheel making 300 RPM? Okay, just do this question. You have, see, the question is, what is the angular speed of a flywheel which is making 300 RPM? So let's do. So who is doing? What is the angular speed of a flywheel which makes 300 RPM? Okay, so find out the angular speed quickly. Yeah, did you get the answer?
15,
Yes.
20, 20.
You just need to convert it. I'm sending some more questions. Just will be getting few more questions. Okay, and in your group, you'll find some of the questions which have been posted. Okay, for this one, your answer would be, what is this RPM? We need to convert it to RPS, revolutions per second. So it has to be 300 divided by 60. So you get 5 revolutions per second. Now this 5 revolutions per second is the frequency. So we write it as F. Now we can find out the angular velocity omega by the formula 2 pi F. So you get the formula 2 pi, 2 multiply pi multiply F, which is 5. So you get 10 pi radian per second. So anyone who obtained this answer as 10 pi radian per second?
It's
Yes, sir.
Okay, Jaswant, what about you?
Yes, sir.
Okay. Now see, you have in the group, you can check question number. Okay, question number 5. See question number 5 in the WhatsApp group. See for question number 5. Okay, so can you read question number 5? See. Read question 5. It states
Right.
the
Question.
angular velocity of a particle, the angular velocity of a particle moving in a circle of radius 50 centimeters is increased in 5 minutes from 100 rpm to 400 rpm. Find the angular acceleration and linear acceleration. So first, just one, how we will do? Yeah, just
So
one.
first, yes, sir.
Yeah, how we will do this fifth question?
So,
Okay, you can see initial frequency is given here. We have the initial frequency.
Yes, sir.
Okay, see, just hold on. I've shared the screen. You have the initial frequency here. Okay, the angular velocity of particle moving in a circle of radius 50 centimeter is increased in 5 minutes from 100 rpm to 400 rpm. Find angular acceleration and linear acceleration. So initial frequency is given to us. We need to first convert it to revolutions per second. Initial frequency is 100 rpm and we need to convert it to revolutions per second. So this would be 100 divided by 60. So you get 5/3 revolutions per second. Now, the same thing converted to angular velocity. So omega naught will be equal to 2 pi f. Okay. It will be 2 pi multiply with frequency, which is 5/3. So you get 10 pi by 3 as the omega naught. Are you getting?
Yes, sir.
So I think now you will be able to do this question. You have got the initial hint and you can obtain this, right?
Yes, sir.
Okay. So bye everyone. You will be only facing difficulty with linear acceleration, that I'll explain it to you in next class. Okay. So bye everyone. Good night.
Good night, sir. Bye.